Okay, so you'll remember yesterday that I was talking a little bit about the famous Galileo demonstration. We tried to drop the two balls. We got reasonable success, although a lot of it is dependent upon that I release at the same time. I showed you the Jay Grampton version, and then we went into the slinky stuff there, right? So we really didn't get too far. I think I went through this, am I right?
Yeah.
Went through the cartoon, which really isn't very funny at all. Right? And then we get into this kind of stuff. So I'm going to go back, just by way of review here, I'm going to go back to this. There are clicker questions. Do you want to get the clickers down? So you ready? Yeah. Come on up and get clickers, I guess.
Notice when you age all
they're coming. They're just sort of built in. This particular lesson, you guys, has a ton of video in it. Okay? So let's go back to the start of this page right here as a bit of a review, and then we'll get into the question. So it says, Galileo showed that falling objects accelerate equally regardless of their masses. This is strictly true if air resistance is negligible. I told you what the word negligible means. It means so small that it doesn't really matter. That is if the objects are in free fall. It is approximately true when air resistance is very small compared to the mass of the falling object. For example, a 10 kilogram cannonball and a 1 kilogram stone dropped from an elevated position at the same time will fall together, strike the ground practically at the same time. This experiment said to be done by Galileo, the leading Tower of Pisa, demolished the Aristotelian idea that an object that weighs 10 times as much as another should fall 10 times faster than the lighter object. You might remember that I said yesterday that I'd be surprised if it was proven that no one did that before Galileo, but people probably just couldn't overcome Aristotle's reputation. Galileo's experiment and many others that showed the same result were convincing, but Galileo couldn't say why the accelerated were equal. The explanation is a straightforward application of Newton's second law, and is the topic of the cartoon back here, which I have there. Let's treat it separately here. So I think this is where I left off. Recall that mass, a quantity of matter, and weight, the force due to gravity, are proportional. That is, the bigger the mass, the bigger the weight. A 2 kilogram bag of nails weighs twice as much as a 1 kilogram bag of nails. So a 10 kilogram cannonball experiences 10 times as much gravitational force or weight as a 1 kilogram stone. The followers of Aristotle believe that the cannonball should accelerate at a rate 10 times that of the stone because they consider only the cannonball's 10 times greater weight. However, Newton's second law tells us to consider the mass as well. A little thought will show that 10 times as much force acting on 10 times as much mass produces the same acceleration as the smaller force acting on the smaller mass. In symbolic notation, there it is. And I'm just going to re-explain that. I go back to this blank one here, right? So we know already that F equals ma, right? And so we can write that as F is equal to, and I'm going to do different colors here for a reason, F over m, right? And the F is the weight force, right? And so if that weight force is bigger because the mass is bigger, right? If both of the F and the m get bigger by the same amount, what happens to the A? It stays the same. Right? If the F and the M both get bigger by the same amount, like say for example, the F was, say that the weight force was 10 because the mass was 1. Well, 10 over 1, if the weight force gets 10 times bigger and it's 100, and the mass gets 10 times bigger, 100 over 10, well, they are clearly equal. Which is why objects fall at the same rate, land at the same time, regardless of their mass. Okay, and it says here, where F stands for the force acting on the cannonball, and M stands for the correspondingly large mass of the cannonball. The small f and m stands for the smaller weight and smaller mass of the stone. We see that the ratio of weight to mass is the same for these or any other objects. All freely falling objects undergo the same acceleration, the same place on Earth. In chapter 2, we introduced the symbol g for the acceleration. So this F equals ma. The a, when you're talking about things that are falling, the a is replaced with the letter g. And on Earth, that value is 9.8 in meters per second squared. If you're dealing with feet, then it's 32. We can show the same result with numerical items. The weight of a 1 kilogram stone is 9.8 newtons at the Earth's surface. The weight of a 10 kilogram cannonball is 98 at the Earth's surface. And the force acting on a falling object is the force due to gravity of the object's weight. Using Newton's second law, the acceleration of the stone is 9.8 over 1, or 9.8, while the acceleration of the cannonball would be 98 over 10, or also 9.8. In the famous coin and feather vacuum tube demonstration discussed in chapter 2, which I didn't talk about, the reason for the equal accelerations was not discussed. Now we know that both freely falling objects fall with the same acceleration because the net force on each object is only its weight, and the ratio of weight to mass is the same for both. And so here's the first question. Get your clickers ready to go. And the question is, if you were on the moon and dropped a hammer and a feather from the same elevation at the same time, would they strike the surface of the moon at the same instant? I think it was Trent that was yesterday talking about, was it you? Talking about a crumpled piece of paper and a flat piece of paper? So we're going to answer that shortly. Okay? But for now, we're going to talk about, let's say, a screwdriver and a feather on the moon at the same time. Now, clearly, if it was, say, just a piece of paper and a screwdriver, which one's going to hit the ground first? Really? I just went through all that math and said that they're going to hit the ground at the same time. Apparently Jason's right. There we go, right? Okay. But if you were on the moon, now if I were Miss Frizzle, I'd have a lot more hair. I mean, we have to fill out a lot of paperwork to go to the moon. But if we were able to go to the moon and do that, what would happen? They would just float there? No gravity on the moon? Well, let's see what your answer is. Yes. Would they strike the surface of the moon at the same instant? I guess Trent's going to have to answer no because he's saying they're going to float. Would they land at the same time? If I went and took my piece of paper and my screwdriver to the moon, on the moon, would they land at the same time? Now, how am I going to answer this question, do you think? And I can give you the answer, but are you going to believe me?
Probably not.
Short of going to the moon, how are we going to do it? I got a couple people left. Will they land at the same time? Yes or no? And the answer, my friends, is yes, they will land at the same instant. Oh. Life sucks. How can I show you this? Well, it just so happens that we have put a man on the moon, contrary to the conspiracy theories. We put a human on the moon, and they actually took video. So here we go. Normal physics, grade 11 physics here. With your clicker, tell me, if a heavy person and a light person open their parachutes together, the same altitude and each wears the same size parachute, who will reach the ground first? I'll let you read that one more time and think about it. Oh, I haven't started this perhaps, right? In fact, I don't think that I've actually gotten to the question. I'll come back to the question. Let me give you the background first. We'll go to here. Yeah, I skipped ahead. Go to here. Falling and everything. So you've seen now You see now what happens as the ball and the feather fall with no air resistance. So how does air resistance work? That's what I got to teach first here. So it says the feather and coin fall, or the feather and bowling ball, fall with equal acceleration in the vacuum, but quite unequally in the presence of air. When air is let into the glass tube and is again inverted and held upright, the coin falls quickly while the feather flutters to the bottom. So normally they do this with a glass tube. They suck all the air out and they drop the coin and feather, and it sort of kind of works, but it's hard to see. That's way more dramatic that they do it. Air resistance diminishes the net forces acting on the object. The net force decreases a tiny bit for the coin and a lot for the feather. The downward acceleration for the feather is very brief because the air resistance builds up quickly and counteracts its tiny weight. The feather does not have to fall very long or fast for this to happen. When the air resistance on the feather equals the weight on the feather, the net force is zero and no further acceleration occurs. I'll say it again because some of you didn't get the cue. When the air resistance on the feather equals the weight of the feather, the net force is zero, and again, no further acceleration occurs. So what I'm saying is this. You drop the coin, you drop the feather, you drop whatever you have, and you have this weight force. Well, it turns out that the faster you go, the greater the air resistance. Now, I'm sure almost all of you have driven down or been in a car going on Main Street, stuck your hand out the windshield, or out the window, and done this, right? Like, who hasn't done that? It's a lot of fun. Will you lose your arm? Could be, yeah. If you stick your hand out the window going down Main Street, what's going to happen to your arm? Not much. But if you stick your hand out going down the highway, you might lose a rotator cuff. Right? How come? You're going a whole lot faster, there's a whole lot more air resistance on your hand, a whole lot more force. Same thing. The faster it falls, the greater the air resistance. Okay, so it starts off small, but as it goes faster and faster and faster, that gets bigger and bigger and bigger. And at some point, those two arrows are equal. And when those two are equal, then the net force is now zero, which means the object is not accelerating. Does it hover in the air?
No.
No. How come? It stays at a constant speed because it's already moving. Already moving. So it just moves at a constant speed. Acceleration terminates. The feather has reached, and there in bold, its terminal speed. Terminal means the end. Any Walking Dead fans out there? Just one or two? Okay, go back a few seasons, Vinny. Remember when they were all going to that one place that was called Terminus? Some people, a little bit more knowledgeable, realize that that was probably not a good place because Terminus means the end. Exactly. As soon as I saw that, I went, oh, this is not good. It shouldn't be going there. If we are concerned with direction, which is down for falling objects, we say the feather has reached its terminal velocity. That is a phrase, a term you need to know. Terminal velocity. It is the fastest speed that something can fall. So if I picked up this ping pong and dropped it, let's go to my screwdriver. If I picked up the screwdriver and dropped it, as it falls, it starts going faster and faster and faster and faster. But does it continue speeding up the whole way? Well, probably to the floor here. But if we went to the senior center that everyone calls the high rise and we dropped it, it would likely reach terminal velocity and it would stop accelerating and just continue at a fast speed, which would be pretty fast. You've all heard the old story or the myth about dropping pennies off the Empire State Building, that kind of thing, right? They call building the CN Tower. Someone will get killed, you can't do it. Yeah, it's a myth. The myth, it's a complete myth. The Mythbusters have proven it. Would you like to see the video?
Yeah.
Of course you would. We'll get to that sometime. Of course you would. Okay, so stay with me here. Air resistance, and with the second paragraph there. Air resistance does not have as much effect on the coin. At slow speeds, the force of air resistance is very small compared with the weight of the coin, and its acceleration is only slightly less than the acceleration of free fall, g. The coin might have to fall for several seconds before its speed is great enough or air resistance to equal and cancel its weight. Its speed at this point, perhaps as much as 200 kilometers an hour, would no longer increase. The coin reaches its terminal speed or terminal velocity. Now, the terminal speed for a skydiver varies from about 150 to 200 kilometers an hour, depending on the weight and orientation of the body. What do I mean by orientation? Their shape, whether they've got their arms out like this, they're trying to slow down, or they're all tightly sort of bunched up. Right? A heavier person will attain a greater terminal speed than a lighter person. This greater weight is more effective in plowing through the air. Body orientation also makes a difference. More air is encountered when the body is spread out and surface area is increased, like that of a flying squirrel in Figure 512. Terminal speed can be controlled by variations in body orientation. A heavy skydiver and a light skydiver can remain in close proximity to each other if the heavy person spreads out like the flying squirrel, while the light person falls 10 feet first. A parachute greatly increases air resistance and cuts the terminal speed down to 15 to 25 kilometers an hour, slow enough for a safe landing. There was a James Bond movie from about 25 years ago where the villain, there's James Bond, no, I think it was James Bond, jump out of a plane. Well, the villain jumps out of the plane, there's only one parachute. So he grabs the parachute and jumps out of the plane. So James Bond has a decision to make. He has to either try to survive a plane crash, or he has to jump out of the plane without a parachute. So he elects to jump out of the plane, and he has to catch up to the guy with the parachute. So how does he do that? Exactly. He literally dives to go as fast as he can, surprises the villain, fights him off, puts the parachute on and survives, of course, because it's James Bond. Right? If you were to, let's say, Anna and Jen decide to go skydiving. Anybody going skydiving in the room? Anyone? Yeah, you want to? I don't know. I won't be doing it. Let's say these two ladies go skydiving, and Anna's got her phone out, right? And Jen pulls the cord. What does the video show that Anna's got?
Oh, it falls out of her ass.
She's got strapped a GoPro, right? What does it show? It shows Jen going straight up. But is that what really happening?
No.
No? How come? Because what? Because Anna keeps going. So they're going like this, right? And then Jen pulls the parachute, and then she goes like this, right? So it just looks like it's your frame of reference. Circling back to that whole idea of frame of reference. Okay, last little bit there at the bottom. If you hold a baseball and tennis ball at arm's length and release them at the same time, you will see them strike the floor at the same time. But if you drop them from the top of the building, you'll notice that the heavier baseball will strike the ground first. This is due to the buildup of air resistance at higher speeds, like the parachutists in the question. At low speeds, air resistance is often negligible, but at high speeds it can make quite a difference. The effect of air resistance is more pronounced on the lighter tennis ball than on the heavier baseball, so the acceleration of the fall is less for the tennis ball. So it's the same reason why the paper and the feather fall slower. The tennis ball behaves more like a parachute than the baseball does. When Galileo reportedly dropped the objects of heavy weights from the leaning tower of Pisa, the heavier object did get to the ground first. However, the time difference was only a split second, rather than the pronounced time difference expected by the fall as the first fell. If it was 10 times heavier, they said 10 times faster. Not even close. The behavior of falling objects was never really understood. The lives of Newton announced the second law of motion. Newton really changed our way of seeing the world. Okay, so now here comes the question. They don't actually land at the same time. No, the lighter one will get there just slightly later. But it's very, very close. Yeah. Unless you've got a big vacuum chamber. Okay, so you know what? We got to go back to question number 1. So now you can get it right, provided that, of course, you remember how to answer it correctly. Right? So this one was, would they strike the surface of the moon at the same instant? Oh, I have a circle too, you're right. I'm still betting someone will get it wrong. Someone might not be listening. Or they'll think it's a big conspiracy and it's going to be wrong this time. Or I don't know. Everyone's finished. Did we get it all right?
Oh my God.
See what I mean? There's always someone. Turner, was that you? Colby?
Yeah, that was me. It dared me to, though.
There's a lesson in that, Colby, isn't there? Oh, wow. If they double dared you, then you got it, right?
I had it right the first time.
Oh, I see. Gotcha. Okay, so question number 2. If a heavy person and a light person...
I can't do it again. Right answer.
Oh, man. What a loser. Okay, that's it. Everyone get it right this time.
Don't check the reaction. Third question.
Don't let me hit stop.
Don't hit stop.
Okay, here we go. Heavy person and a light person open their parachutes together at the same altitude and each wears the same size parachute. Who will reach the ground first? This is tricky. Let's read again. If a heavy person and a light person open their parachutes together at the same altitude and each wears the same size parachute, who will reach the ground first? Heavy person, light person, same time? Impossible to tell. And the answer is down here in the fine print right there. I'll just make it bigger right away. Well, after we answer the question. And then I'm not hitting stop, right?
No.
Going on to the next one. Not hitting stop. I'm not hitting stop. Hunter, what do you say? Come on, man. Okay. What about if the force of air resistance is the same for a falling baseball and a falling tennis ball? Which will have the greater acceleration? These are both questions that are on the back side, right? Well, the questions are there, the answers are not. If the force of air resistance is the same for a falling baseball and a falling tennis ball, which will have the greater acceleration? Baseball one being slightly heavier, right, than a tennis ball, probably about twice, which will have the greater acceleration. They're not easy questions. It's okay to get them wrong. Okay, back table, boys. Okay, how many people got the... Oh, really, you guys? Still number one? Okay, the answer here is A, the heavy person will reach the ground first. Here's the explanation. The heavy person will reach the ground first, like a feather. Going to make it bigger? Like a feather, the light person reaches terminal speed sooner, while the heavy person continues to accelerate until a greater terminal speed is reached. The heavy person moves ahead of the light person, and the separation continues to increase as they ascend. Why does the separation continue to increase? Because one is going faster than the other. They're both going at a constant speed, but one is going faster than the other. So it's going to get farther and farther and farther apart. And if the force of air resistance is the same for a falling baseball and a falling tennis ball, which will have the greater acceleration? The answer is A, the baseball. Why? Because the baseball is heavier. Okay? Don't just say the same. It's true that the air resistance may be the same for each, but that doesn't mean that the net force is the same for each, or that the ratio of net force to mass is the same for each. The heavier baseball has a greater net force and a greater net force per mass, just as a heavier parachute is previously considered. Okay? Not easy questions. I'm going to post that up to Schoology if you want to read that again. It's not that important. What do you need to get out of this? The objects will fall the same if the air resistance is 0 or negligible. You should also know what the idea of terminal velocity is as well. Those are the two key things that you should get out of that. Okay, now there's a couple little demonstrations as well.